So good afternoon. I invite you for the last lecture from the computer architecture course. Today's lecture is about a development of processors, mainly focused from the time on when the first processor has been integrated on the single silicon chip. So there has been even the previous incarnation of the processors and some computational machine, but we focus on those development when the chip was big enough to implement the whole processor. For introduction, I have there some nice picture of one flower from our countryside, so you can enjoy the spring and so on. And now we get to our processors. There has been a team from Fairchild, if I remember, which was able to implement the first processor on the single piece of silicon, but one of famous and known processor of that era was Intel 4004 processor, which was a 4-bit processor. At that time, there has been a relatively big processor, even Unix operating system and so on, but those run on the big computers, which has a processor built from many discrete components. And this one from the Intel company was a chip which was initially intended for the home appliances, for microwave ovens and so on. And it was small chip which has something like 2000 transistors, was 4-bit and has 1 kilobyte of RAM memory, but accessible by the 4 bits quantities and 4 kilobytes for the program. And it has run on sub 1 megahertz frequency, and price was $200. So if you see the price at the chip introduction, then it didn't change too much, even that the level of integration changed in the time very lot. Today you have 1 milliard, in meaning 100 milliards of the transistors on the single chip in the long scale English notation. So it is, for example, Xilinx versatile system. So if we go to that start, then Intel introduced later the 8-bit processor, 8008, and then a famous 8080 processor, which was 4-bit processor. There exists a CPM operating system for it, and it has been used for a relatively long time. If those small processors, which has 8-bit registers, use pairs of the registers to allow to access at least 64 kilobytes of the memory. Because if you use only the 8 bits, then you have only 256 locations. It has additional address space for the input-output peripherals. So for input-output, you have separate space for 256 registers. It is interesting that this processor has 8 registers, but there was another company, NMOS Technologies, which started with the processors which has only 2 or 3 registers on the chip. So it was an alternative. Then Intel came with 8085, and Intel developers team has, for some reason, has leave the company and found another company called Zilog. And Zilog 80 was very famous processor for the Intel Spectrum 8-bit computers and so on. So it was at that time quite useful architecture. Anyway, Zilog company tried even to build a bigger processors, but unfortunately, even that the design was relatively well defined, they didn't succeed because Intel has much more business momentum with their chips. And then Intel tries to implement and refine the complex processor. I think that it was i432, which was big processor, which should solve even the memory management in the hardware and so on. And it didn't fit on the single chip. But the management of the company decides they need some processor now, so they make a pressure to the developers and they designed 8086, which was in the fact extension, 16-bit extension of the original 8-bit 8080. And we keep this legacy in the 8086 architecture till today. In a parallel, there was a company, Motorola, which started with some small 8-bit processors, but came with Motorola 68000 processor family. And it is interesting that it is almost at the same time, but it was the processor which was internally 32-bit. So it has a 32-bit registers, and it was much more straightforward to use and allow to extend to even more modern system. But 8086 has been chosen by the Intel, by the IBM for the IBM PC because it was cheaper and they got some licenses from Intel for this, for the production of the clones of this processor, which was not an option for the Motorola. So at the end, 8086 has win, but it was only a 16-bit processor, which was extended by that complex system of segment that it can address 1 megabyte. And only later it was extended to address 16 megabytes, but still not as a 32-bit processor, but as a 16-bit processor to 286. And if we compare this, there was a Motorola 68020. It was modern chip, which allows to add the external memory management unit and so on. So it was, in the fact, a better processor at that time. Then Intel came with 8386 processor, which was their first really 32-bit processor with 32-bit registers. It allows to address 4 gigabytes of the address space and has a memory management unit on the chip. Motorola has provided something similar, 68030, which was relatively nice processor with 32-bit address bus and so on. Then we have there 486 from the Intel, which add on the chip even a floating point unit. So it was a single chip which can compute even the floating point arithmetic. Previous chip needs to emulate the floating point arithmetic or use external chip as a coprocessor. Motorola has provided 68040, which has a floating point as well. And then it was enough space on the silicon that IBM and Motorola at that time can port original power architecture, which is much more old, but it was from the mainframe computers, from the big computers built by IBM. It could be a shrink to a single chip, like under the name of PowerPC. And it was interesting that it was 32-bit processor, but with 64-bit bus, and original Power was even the 64-bit system. So there was really fast extension to the 64-bit system from the PowerPC and so on. Then there is some Hewlett-Packard Parisk system and so on. And you can see that we are on something like 60, 50 megahertz at that time. And those original processors was a microcode implementation, so they usually need more cycles to execute a single instruction. At the time of Pentium, Intel built their first superscalar CPU, which was able to execute in optimal condition up to 2 integer instructions in single clock cycle, and has even the parallel floating point pipeline. So it was already a superscalar. Then we have there a very interesting alpha from Digital Equipment Design, which was very well thought architecture, which has a perspective to be leading for 20 years, but due to the problems with marketing and so on, it didn't catch. But it was a really modern 64-bit processor on the single chip with relatively large cache and full virtualization and so on. And it was again a RISC-based. Then we have there 68060 from Motorola, which was still compatible with original Motorola 68000 with a single instruction set without no need for some switch of the mode and so on, because original processor has been 32-bit one. And this one is interesting that it implements a complex instruction set in the fact in the RISC-like core. So it was a pipeline processor, superscalar with branch prediction and so on, and it was relatively interesting at that time. But in the PC market, Pentium prevails. There was Pentium Pro, Pentium 2, then a Pentium 4, which was tuned and implemented for very deep pipelines and increase of the clock frequency. But it was not so much useful at the end because it has so big power consumption that Intel then returned back to the Pentium 2 mobile version and started their Core and Core Duo and so on architectures. In the parallel, the Power architecture develops as well. The Power is based on that original design of IBM. It goes to 60s or very old time, but in this case on the single chip, and in this case we have already processor which has 64-bit registers and 128-bit addressing capabilities. Okay, so now we look at that adventure how the processor designers think and implement a processor on the single chip. So if we return to that 4004 and those simple 8-bit processors later, they has been focused on the accumulator architecture. This means that into 8-bit opcode, because you have only the 8 bits to encode the instruction, you cannot encode, for example, if you have more than 2 or 3 registers, you cannot encode a 3-operand instruction for the 8 registers, because 3-operand format with 8 registers 8 registers are encoded by 3 bits. It would need only for encoding of the operands 9 bits, but they do not fit into the 8-bit of the instruction. So they decide that there is only the move instruction, which has 3 and bits for the operands. So it can move from arbitrary register to arbitrary another register. And the rest of the operations has only the single register specified, and the another register is accumulator, which is implicit. So basically you can add value to accumulator, store accumulator to some location in memory, and so on. So it is relatively limited. So those are those accumulator-based processors. Intel has started from the start with the processors which has implemented call and return instruction which directly store a return address, 16-bit return address, because it has 16-bit PC, onto the stack, top of the stack in the main memory. And because for the addressing you want to work with 16 bits at least to address at least 64 kilobytes of the memory, they decide to form the registers into the pairs. So basically you can use a pair of the register to address a location in the memory in whole 64 kilobyte range. And to speed up some operations, there was a 16-bit increment operation and even some addition that it was possible to do by single instruction to add two pairs of registers together. And it was programmed, so each instruction took from 2 to 11 clock cycles. So if you compare it with today processors which are able to execute up to, for example, 6 or Apple M1 up to 8 instructions per single clock cycle or finish execution, then it was really much slower processor. There is the internal architecture, so you can see that there is that accumulator. I should locate it. Okay, there is the accumulator. So it is that register which was implicit input to the arithmetic logic operation. Then there was another temporary register. So basically you can say, I want to add accumulator with some of those registers from the register file. So you take, for example, B register, deliver the B register to one input of accumulator of the arithmetic logic unit. On the other input, you deliver the accumulator, get the result, and the result was implicitly written to the accumulator. There was, as I have said, only small number of the instruction which can directly, for example, increment a register pair H, which is high part, and L, low part of this pair register. What was interesting on this architecture is that in the fact we have there 6 standard registers, 1 accumulator, and the last combination of the bits encoding a register informs that we want to access a memory location which is pointed by HL register. So it was relatively interesting in this respect. But it was really slow, 8-bit, and so on. On the other hand, Motorola and NMOS technologies started with different idea how to implement a processor. They implement the 8-bit processor which has only the accumulator AB, then some index register and stack pointer and program counter on the processor. So it has even lower number of the registers, but because it doesn't need to reserve so many bits from the opcodes to specify the register, they can implement more addressing modes. So they have the addressing which allows to addressing through the index register plus some location in the memory and so on. So it was relatively interesting to enhance a number of the registers or fast accessible locations, it uses a 0 page. And those 8-bit processors, same as 8080, allows to specify that you have opcode, which was 1 byte, and then to have the additional bytes which specified, for example, the immediate value or memory location and so on. There is one interesting processor from Texas Instruments, it was 990, which has no registers directly on the chip. On the chip there was only the workspace pointer, which points to a location in the memory, or we can say that it has one register on the chip, and all the other information like the actual program counter value, actual stack pointer value, and so on, was held on that task state structure in the main memory. So it has big advantage that if you want to switch from one task to another task, that you do not need to save and restore registers, because registers has been already in the main memory, and if you want to run another task, basically you have only to move the destination in the workspace pointer, and another program, another parallel thread has been run. On the other hand, this means that you need to access memory very often, so it is expensive in the number of memory accesses. But at that start, memory was slow, but the actual instruction processing was even much more slow. So it was not so big problem. Then the speed of the processor execution started to enhance. And the initial processor has been built such a way, we try to build something on the silicon which fits there and is Turing complete. But basically they didn't think about a higher level languages. Even that C language is from 70s and so on. But the initial processor has not directly supported, for example, local variables on the stack and so on. Zilog Z80 has provided some support for the indexing against register pair and so on. So there was some changes in this direction. But then there came the era of complex instruction set processors, which tries to support a similar addressing and features which has been modeled according to the C language. So it tries to be supportive to the programmers and provides instruction set which can process as much by single instruction as possible, because at that time it was a problem to read more instruction from the memory, because it was a narrow bandwidth between the memory and processor. So they decide if we have so clever instruction which can do a lot in the single operation and it will match C program line, then it would be a great. So, but in the case of 8086, they still keep the compatibility partially with the original 8-bit design and keep a number of registers very low. So they keep from that 8-bit registers, they form 4 pairs of the 16-bit registers and added the additional 4 16-bit registers which support access to the stack pointer, bottom or frame pointer, so you directly see the connection to the C, source index and destination index registers for that block memory transfers and so on. So if you see this this set of the registers, then you see that they map quite well for a C program. And the address space has been extended to 1 megabyte, but not by adding or extending size of the registers, but only by allowing a multiple 64 kilobytes segments to be allocated from 1 megabyte address space. And those processors provide already a little more on orthogonal instruction set, but because into the 16-bit we do not fit with 3-operand instruction well as well, they decide that one of the operands is source and destination, and another is source. So basically we have 2-operand encoding of the instruction, and typically they can do the register plus or minus or some another operation with the register, or it is possible to add value in the register to the location in the memory, or it is possible to take value in the memory and add it to the register. So basically we have all these options, and it can combine a memory access and even very complex memory addressing modes to access a data in the memory and add it to the register or directly modify the value in the memory. Motorola 68000 is similar, but started with 16 32-bit registers. They have been divided to 2 groups. We will look at it later. And it has 2 operands encoding of the instructions as well. And again, they can provide a register plus register for 2 operands, memory plus register, or register plus memory. So basically those combinations that one operand has been fixed that it is only the register, and the second operand can be a register or a memory. And there was even one operation which can move data from one memory location to another memory location, but it was only that single operation. But thanks to the relatively complex addressing mode, it was possible to use it a similar way as on Intel for those string operations, because you can write that pointer plus plus, for example, post increment location should be assigned from the location pointed by register R, which is again post incremented, for example. So you can write or rewrite such C code directly to the single instruction. And if you put there a tight loop command, then again you have an instruction which allows to move a block of the memory. What was still the problem of those processors, that they has been a microcode based. So it is interesting that Zilog has provided later, but not so much later, a complex instruction set processor, Zilog 8000 or 80000, which has been a 16 and 32-bit, but they process the instruction without the microcode in 6-space pipeline. So it is interesting, and what is interesting that this Zilog implementation has only the 18,000 of the transistors, and Motorola 68000 has a roughly 68,000 of the transistors. So it is interesting that even at that time it was possible to build a pipelined processor, but it was not commercially useful. Okay, we have seen our x86 processors already, so we can see that this one, this way, in the fact, with AL, is that 8080 processor. Then they extended to 16-bit and added another 4 registers to access location in the memory and on the stack and so on, so to be well prepared for C-language programs and so on. Then in the case of 386, the registers has been extended to the 32-bit. And still the number has been kept on that 8, and only during the extension to the 64-bit we get additional registers. As you can see, if you compare it with the RISC-V or MIPS, there is a status register which is used for a result and of the arithmetic logic operations. So you have that conditional branches and so on, based not directly on the comparison of two registers inside a branch instruction, but you need to use a result of previous arithmetic logic operation or compare operation or something like that. We have their program counter and those famous segment registers, which are in the fact not used in the modern operating system, 32-bit operating system usually. And today, even on the 64-bit system, they have been omitted almost altogether, except for some base for the thread local storage. Okay, so there is an alternative. In the case of Motorola 68000, they started with clean 32-bit architecture, but they divide registers to two groups, one for the addressings and one for the data. So this one is for the addressing and the another one is for the data. And for the data registers, they decide that it is possible to access them by byte, 16-bit or 32-bit. But for the addressing, they decide that it is enough only the 16-bit access and 32-bit access. And in the addressing mode, you can specify that you want to use the addressing register as the base, and you can add the immediate value or the data registers as the index. This processor has predefined a stack pointer register, which is register A7, and from the start, which is very important, they have two copies of the stack pointer. One copy of the stack pointer is for the user mode, so basically when the program runs, and at the moment when there is a call of the operating system, some exception of this call, then the processor automatically switch to the system mode and switch to another stack, which is very important because at the moment when the processor stores a return address to the stack and state, even at the time when you switch to the system mode, then it is important that the user program state is stored on the system stack. Because if you have a location specified by the user stack where you store the information about the exception, then in this case there can be a problem that user stack points, for example, to the page which is at given time not present in the memory, and if you try to resolve the exception and store the state onto the user stack in such situation, you have double fault and it is not possible to do anything. So at the moment when you want to have the system which allows to separate users, limit their access to the memory and so on, it is necessary to have two modes, and in the system mode you need at least some location where to store the previous state of the processor, and in this case it is a supervisor stack pointer. So at the moment when we switch to the user mode, from the user mode to the system mode, this second stack pointer started to be addressed as a A7 register and so on. For the branches, this processor follows that stuff of complex instruction set processor, and it has a condition code register, and a lower 8-bit of these registers stores information about result of previous arithmetic operation and allow to branch on the negative result, bigger, lower, and so on. And what is interesting, if you assign to the data registers, then condition code register is assigned and set. If you increment or add to the address register, then it is expected that it is only the manipulation with the registers, with the pointers, and in such case, we do not assign the conditional code. And at the moment when you switch to the system mode, then the conditional code register is extended by the status bit. So we can see here what is the typical organization of the processor's status register for those processors of this era. So we have there the information. If there was unsigned overflow or carry in the previous arithmetic operation, if there was an overflow, if the arithmetic logic operation result with the 0 output, negative output, and that extended bit is used if you want to build, for example, 64-bit addition from two 32-bit additions. And this part is accessible in the user program. And in the system mode, there is another set of 8 bits. When one of those specify if we are now in the user or system mode, for sure, user cannot set this bit on. And then there is a mechanism to mask priorities to some level. So basically, you can have even the nested interrupts. There are another bits which allow tracing. So if you want to build a debugger, then usually you want to build it such way that it can do a single step of the user program. So in such case, a system sets the copy, those trace bits in the copy of the status register, which is loaded by the processor when you return to the user program. And if this bit is set, then the processor executes exactly the single instruction, and then there is again the exception, which is intercepted by the operating system and delivered to, for example, through ptrace to the debugger, GDB, and so on, running as another process. And if we look at the 68000 family, then it is much more orthogonal and simple to understand than the Intel. It has up to 14 addressing modes, and we can start with the addressing by a register. In such case, the register can be a data register or address register, or we can address a location which is pointed by the address register. But we have there even the option that we can address the location in the memory and say that this addressing is with post increment. So basically you read the value or write the value, and then the pointer is moved by the size of the pointer. You exactly see the pointer and plus plus operation on the C. You can have a predecrement. It is not fully symmetric in this case, or it is in the fact symmetric, that you can build a stack. So basically, if you do a predecrement and store the value, then the inverse operation is to take value and the increment. So basically, you can build a stack in this case from arbitrary register, but register A7 is specified by the hardware that it stores a return address in the case of branch to subroutine operation. Then you can combine the address register with 16-bit offset and a combination of address register plus any register used as the index and 8-bit offset. So this can be encoded into the, I think, into the two 16-bit, yes, two 16-bit words. So those instructions can fit into the single 16-bit operation. Those need two, so it is 32-bit in the fact, 4 bytes in the memory. Then there is the option to use the absolute addressing and even a 32-bit absolute addressing. So in this case, such operation needs 48 bits or 6 bytes. And later, there was added much more of the complex addressing modes, which allows even to combine the address register with the index register, which can be multiplied by 1, 2, 4, or 8, and add the base offset, and this base offset can be even up to 32 bits. So in such case, we can have really complex instructions executed by this processor. But because the encoding was relatively clean, orthogonal, that this addition of the addressing modes was possible without the need to change the instruction format. So it was, I think that it was much more clean than the x86. Amiga computers based on 68000 and even some Unix workstation was much more powerful at that time and clean than Intel chips. But later the Intel has speed up the hardware and so on and prevails. Anyway, we have used a complex instruction to encode the instruction to lower the amount of bytes read from the instruction memory. But we still have problem with throughput and access of the data memory. So for this reason, we need somehow to speed up memory access anyway. And at that time, there came a concept of the caches, and usually a separate one for the instruction and data, so in the fact hardware caches, and later multiple levels of the caches. And this solves the problem with throughput to access reasonably programmed algorithm to access a main memory, because you can use that working set in the cache. On the other hand, you start to have the problems with coherency between the caches, main memory, and if you have a symmetric multiple processing between the multiple cores. So you need to add some special instruction to provide barriers which ensures that the data are delivered from the processor to the cache and then from the cache to the main memory. If you want to run a symmetric multiprocessing with standard thread model, you need somehow to resolve a synchronization of the caches. So I have there the example of the modified overt exclusive shared invalid protocol. So if you have two caching agents, so it can be, for example, two processor cores, and each has its own cache memory, then if we want to run a standard program which expects that the access to the single location is coherent over the whole processor cores, then you need to specify rules. If a given address is cached only by a single cache, so basically in the another one it is in the invalid state, then there is no problem, and a given processor can use any state of the cache. At the moment when the another processor, for example, wants to read a memory location, so it wants to read the same location, there is a same location read by this processor, then in such case we need to inform this cache that there is, through some snoop operation, that there is attempt to read the location, and if it finds that it has, for example, a modified data in the cache, then it needs to move to the state when it delivers a modified data to the memory, or it delivers a data to the another processor directly, and we stay in this state. Basically, we cannot be in the modified state any longer. So if one processor has modified data and another accesses the same address, then it is necessary to switch to this state. If this another processor wants to modify the data, wants to write to the data, it needs to switch to the state when the data are modified, and in this case it needs to ask this processor to go to the invalid state. So basically we need to move to this state when the another processor is in the invalid state. So we can share only data in the case when they are not modified. At the moment when they are modified by a given processor, the other processor has to be in the invalid state. But sometimes it is, if you read the data, you do not know if you want to share them with other one or not. So if you other the state that you read the data which are not in the cache of any other of the processors, then you can stay in the state exclusive or owned. Because you know at the start that nobody else has a data. And if you are at the state exclusive or owned, then exclusive, then you can move to the modified state without need to inform the other processor that you go to the modified state, because at the moment when somebody else wants to access the data, you can be sure that you have already moved to the shared state. So this is for free. Same if you have a modified data, you can keep the data in the state owned, in which state you deliver a data to other processors in the system which do not need to access main memory. So it is optimization and speed up in this more complex protocol which allows to deliver data from cache to cache, because this is often much faster than to store the data to the memory and then to read them by another caching agent. In the fact, today the actual architecture, even on the single chip, is in the fact based on the rings. So you have there a cores, up to, for example, in this case, we have there something like 16, 17 cores. And those cores together and their caches are connected through the rings. So in the fact today, the communication inside the processor works a similar way like the communication on the network. So to check that nobody else shares the same data is relatively expensive task, and you should be very clear when you share data that you share data which you do not modify, or if you modify data by a given thread, then there should be no other thread which use that data at all. For sure, you need to have there some mutexes, semaphores, and so on. So you cannot eliminate all data sharing, but it has to be minimalized because all access and to the shared modified data is very, very expensive. Anyway, we have speed up a memory. And now the execution of instruction started to be a problem again. So there was attempt to reduce the execution time of the instruction and allow their pipelining and clean load store architectures and so on. And there appears a more reduced instruction set processors. So there has been attempt to define a simple instruction which can be executed faster. The order of the execution is defined by data flow dependencies, so they are executed out of the order. For the branches, we have there a speculative execution, and the actual computation is modified to the computation only between the registers, and a separate instruction for the memory access. And some of them eliminate code or status word conditional registers like a MIPS or RISC-V, which do not have a conditional code at all because they use directly register comparison directly in the branch instruction. Or some processor like PowerPC has multiple flag registers, and you can specify, for example, that if you use flag register 0, that basically there is no dependency because result flag of the operation, arithmetic logic operation, is put into the something like dev null, basically to the register where it is discarded. Or some processors like ARM has the option to suppress flag update for the operation, so again to lower interdependencies between the instructions. So we have those sometimes strict load store architectures. They have only a very limited set of the instructions to load and write data, and the actual computation is done only between the data, between the registers. And because you have lower complexity of the encoding of that accesses to the memory and so on, there is usually space to encode more registers. So RISC processor has usually 16 or even more 32 general purpose registers. And they started with fixed encoding, usually 32-bit, which is a little waste of the memory, and it has a demand on the little bigger caches and so on, but the execution can be much, much faster. So we can start to use pipeline execution, which we have seen in our course. For example, that is this famous 5-stage pipeline, which we have seen on the MIPS and RISC-V, but it can have even a different structure. And sometimes to resolve the problem with the branches, they define a delay slot. So basically, if we have branch here decided in the memory state, that we execute one or sometimes even more instruction after the branch unconditionally, which still can be a problem. So then there is a switch usually today to the branch prediction, which tries to limit and decrease the number of instructions which has to be flushed. So today the typical processor look like this. There is some fetch stage which use information from the branch predictor. Then there is a decode. Then there is a dispatch to more execution units. Sometimes those execution units has reservation station assigned to them, or other option is that there is a global shared reservation station location, and we deliver the instruction to a given execution queue when all the required input arguments are available. So basically we execute the instruction out of order, but because we want to have a precise exception model, we need to reorder them and their global state and architecture state effect according to the original order. So it is necessary to resolve the exceptions that basically you can restore the state which corresponds to the sequential execution up to the instruction which causes the exception. So we need to reorder the instruction back here, and then there is completion and retire and store buffers and so on. So this is how modern processor looks like. If you want to know more, we have advanced computer architectures course here. Okay, now to the different techniques. So generally we have more registers for the RISC, typically set 1 plus 1, so that one register is 0 register. So you can use a register which provides a constant 0, which simplifies the instruction set. So for example, you do not need to have a separate instruction for the move, because you can use a register 0 which provides a 0 and so on. 32-bit ARM has only 16 registers, which is a little less. 64-bit ARM switches to 31 and 1 register as well. But if you compare it to the 32-bit mode of 386, which has still only 8 registers, then it is sure that Intel needs to reload and spill and so on the data between the stack and the registers much more often than for the RISC architectures. There was some another attempt how to lower number of accesses of the memory which use register windows. So it is a different attempt than the cache. In the fact, it is more deterministic. It is a mechanism which is still in use in the processor, for example, for the space application. And it uses a little different concepts, how to call the subroutines and so on. We look at it a little later. So basically, you have up to, for example, 100 of the physical registers, but at given time, only 32 bits or 32 of them are accessible to the user, and you move the registers when you call the subroutine, then you move to the next window. Some another processors has defined that if we call the subroutine, we do not directly store the return address on the stack, but we put it only to the return address or link register. And this ensures that if we have there some call graph, basically, if we from some functions we call another functions and so on, then it means that because the leaf level, those last functions are called and the return address is stored in the register, and then we return from this instruction, from this subroutine, then we do not need to store the return address for a leaf node function to the memory. We need to store it when we call from one function to another function, because in another case the register is overwritten and we do not know where to return. But in the case of this link register, in the fact we move that memory access one level in the call graph to the root when if there is unconditional move of the return address to the top of the stack. Okay. The RISC architectures and PowerPC has, as one of them, has interesting concept that basically they specify what is not declared by the manual, that it is supported, is undefined. On the Intel, the typical use was to use as much as possible from the instruction set, and Intel needs to keep the compatibility with all the different clever or hackish use of the processor from the DOS days and so on. On the other hand, for example, PowerPC specify this is the user architecture, and only this set of the floating point register and general purpose registers is available for the user, and only this concrete mechanism, how they behave and so on, is defined. So in the fact, thanks to this strict definition of the user architecture, it was possible that even programs from the 80s can be run on the latest version of the PowerPC and so on. And for the memory synchronization and so on, there is a defined memory model virtual architecture, and then later there is defined supervisor, but it is fully separated. So if you want to run the programs on a newer chip, for sure you need to update or extend the operating system, but user program can be kept in the same form. And for example, PowerPC is still quite useful. Those big power chips are used in, for example, Oak Ridge National Laboratory supercomputers. So this is first computer in the rank top 500 computers, most powerful computers on the earth from the year 2018. And you see that it is based on the PowerPC architecture. There is some, I am not sure if it is water or neon cooling. It is combines those powerful processors from IBM with on each node those two processors with 6 NVIDIA Volta GPUs, and you see that there is quite fast PCI Express connection. And then what is very interesting, there are NVLinks which connect a CPU with GPUs and GPUs together, and they are really fast. They are able to deliver 100 gigabytes per second. So all the 1 terabyte hard drive capacity can be, in the fact, internally delivered from one chip to another at 10 seconds, which is quite fast. And today they have even the newer version. So this NVLink is running on 40 giga symbols per second, I think. So basically, this is the frequency which is run on the single lane, and you can combine, same like for the PCI Express, more lanes in parallel. So it is really able to deliver 100 gigabytes per second. There is some specification for the memory, so you have 2 terabytes per node, and you have some non-volatile memory per node, and the actual storage of whole system is 250 petabytes. What is interesting that the power architecture is built by silicon on insulator process, which is quite modern, and it can run up to 96 threads, hardware threads, on the single chip, because it is 24 cores, but each of them can run up to 4 threads simultaneously. Only the cache memory is 120 megabytes, and so on, and speed is very fast. On the other hand, if you look at that older time and on to the Spark, then in that time they think that it is problem to access a main memory, and then try to define the model which doesn't need to access a main memory so often. In the fact, a RISC project was started by the Professor Peterson, which is that famous professor which written a computer organization and design book, which we use as a base. So this is his design with his students, and we look at the mechanism. So we have 32 registers. One of those registers is fixed as 0, if I remember well. 8 of them are global, and the rest, the 24 registers, are divided into the groups. And the group has 16 registers, but has overlap of the 8 registers with previous group. And I probably skip the description, and we look at the actual encoding. So you have there 32 registers. One register is 0, it is fixed. Then we have there those 7 global, which can keep some data, which are kept even over the call of the subroutines. And then we have there the local registers for a given level of the program. Then we have their output registers, where we can store up to 6 arguments to call the subroutine. And then there is a space where we store the previous stack pointer. So this is that store bottom pointer, move stack pointer to bottom pointer, this combination which is done on the Intel. So this combination is done even there, but we have the separate stack pointer here. And then there is a return address. And at the moment when we call the subroutine, then those registers in the fact move there, as the 6 input arguments to the function, and new set of the 8 local variables, registers, appears to the given level of the subroutine. So basically it works like this. We have there the locals, we prepare the outs, so input arguments for next level, then we call the subroutine, and this wheel moves by 16 registers, so the next subroutine has the 8 local registers, and outputs appear as the inputs. And again, if we call the subroutine, we can move this way data because those output registers became the inputs and so on, and we do not need to access any stack up. We fill a whole hardware register. At the moment when we want to call from that inner function, in the fact 7th function in the call chain, no, 6th from this. At the moment when we want to move there, then at this moment we start to overlap out registers which the in registers of the 7 calls below us. So basically we would lose the data. So at the moment when this wheel moves too far, then at this moment we need to save data. So there is exception. Operating system ensures that this part of the data, in the fact this part is stored into the memory, and this can run. And again, when this calls another function, then again there is overlap with this, so this has to be stored into the memory. And when we go back by the returns, and we again reach the limit of those levels of the function calls, which has been already stored to the main memory, then there is an exception, and we need to restore the registers from the memory. But if you look at it, if we have that call graph, then basically if we call the subroutines, then we call no problem, no problem, no problem, and only when we reach a recursion or the call depth of 6 and want to switch to the 7, then we need to store the data from the top level function to the memory. And then when we call this one, we need to store this. But as you can see, it is very old data, and if we expect that there is fan out, that one function calls more functions than one, or maybe even in some loop it calls many functions, then in the fact we save or do not need to store data for many calls. So basically we can do all this then without storing the data, and only when we return to the second most top level function and then to the top level function, we need to restore data only once. So instead of the store and restore of the return address, stack pointer, and so on, for each function, we need to do it, for example, in this example, only twice, which is much, much better. Okay, as for the Spark, it has been used even in the big system, and still it is produced by Oracle for some database servers and so on, but it is not so common architecture today. But in the space, there is a Koban Geisler implementation. It has open source Leon chip, or Leon design, and then it is not open source but closed source Leon system, which is integrated on the silicon. And it has floating point unit up to 4 cores. Those cores can be divided even to the mechanism that 2 cores form a lockstep system for the high reliability, that everything is computed 2 times. It has second level cache. Interesting is that this second level cache can be coherent between the processors and peripherals. So it is in the fact caching a memory interface, not directly the processor. And it is a system which is used for the space flight. So there is the such system, photo of such system. Problem is that it is very expensive. It runs, for example, RTMS operating system, where I have led more Google Summer of Code project and so on. So you can even work on operating system which is used on those processors. For sure, you probably would not program for this processor because this processor price is in the $10,000 per single chip, or even much more, because it is very expensive. Okay, if we return to the MIPS, it was a design of Professor Hennessy. So again, another of our professors who started the modern processor architectures teaching and so on. Then it was much more simple. It has 32 registers, one is fixed 0, and it doesn't use Windows and so on. So it is much more simple. It has been in the base of the silicon graphic computers, so it was a processor on which the first OpenGL and 3D graphic has been developed and so on. But then it loses the momentum, and today it is quite often used by Chinese computers. There are small MCUs, microcontrollers, based on the 32-bit MIPS instruction set, or even that subset. Some of them cost something like 50 crowns per one. So it is relatively cheap, and you have in the fax, okay, the chip which was in the past a chip or heard of supercomputers. And there are some examples of 64-bit chips. It is used in FPGAs and so on, and it was used as a model for many other similar processors from different companies. And they decide that they do early jump instruction decode, and that there is a delay slot, so that they execute one instruction after the branch unconditionally. Today, when we have a full out-of-order execution and branch prediction, it is not so big win. But at that time, it looks interesting. Today, we resolve this by the branch prediction. And if it is the branches which can be predicted, then it is correct. If you have the branch which is dependent on the actual processed data, as I have shown for that image processing, then it can be a problem. There is Longson 38 MIPS-based chip from the Chinese Academy of Sciences, and it is interesting that it has the registers for multimedia or vector operation to the width of 256 bit. As you can see, it has branch predictor, TLBs, and all that stuff, decoder, and it can decode up to 4 instructions in the single clock cycles. That has fixed point queue registers and 2 arithmetic logic unit running in parallel, and address generation unit for the memory accesses, which is shared for the floating point and the integer part, and then 2 floating point subsystem which can compute the values. And then there is again data caches and some other stuff. So this is the 64-bit MIPS machine with and on the server which has 8 of such chip. And each of them has 4 cores, so it is a relatively interesting architecture as well. And they are preparing the chip which will have 16 cores on the single chip. On the other hand, if we have those RISC processors, there is some problem that the fixed encoding of the instruction to the 32-bit has some overhead, and mainly for the small embedded application where you want to keep instruction in the flash memory, it is problem with capacity of the flash, and for the big ones it is problem with capacity of the caches, that you do not fit enough of the code in the cache, and that you need to big flash, so it is a little more expensive. So for this reason, even the RISC-based CPU started to encode some subset of the instruction in the 16-bit aliases. So they started with 32-bit instruction, but for example, for the ARM, you can switch for given function. That given function is not implemented in the full 32-bit ARM code, but that it is implemented only in the 16-bit so-called thumb mode. And today, even those Cortex-M chip, which you know from the STM and Nucleo and such stuff, if you know some small MCUs, then those use only this 16-bit subset aliases with some extensions that it can run the control instruction and so on. There was another, okay, for the MIPS we have that Aptiv with 16-bit encoding. Then there was MCore, which was strictly using 16-bit encoding of the instruction, but in such case you have no possibility to store the immediate operands, wider immediate operands in the instruction. So it needs to use PC relative addressing to access the constant in the memory. So it has some problems. Another 16-bit only encoded instructions is Super H. There was interesting approach from the Motorola or Freescalator, which is called Coldfire, which used that original complex instruction set architecture, which has all that complex addressing modes and so on, and they decide to implement it as a RISC processor and specify you can use those complex modes, but the instruction cannot exceed 48 bits, so 6 bytes, because if it is longer, then it would be problem to decode it in the embedded system and so on. So they do it this way and implement it in the fact RISC processor with complex instruction set. Anyway, Intel has to switch to RISC implementation as well. So internally today, Intel chips are more RISC than the original complex instruction set, and there is a hardware translation of the instruction on the fly. Then what is interesting on RISC-V is that it is a processor which has a 32-bit encoded instruction, but they reserved 3/4 of the code space. So basically they left only 1/4 for the 32-bit instructions, or a little less because there is even the space to encode even longer instruction, and left the 3/4 unused. And those 3/4 was later used for the 16-bit encoding of the aliases of some instructions. So it has big advantage that you can combine freely 16-bit encoded and 32-bit encoded instruction, which is not possible on ARM. Okay, if you look at the ARM, then ARM was initially designed by Arcorn for the Arcorn computer, Advanced RISC Machine company, and it used 16 registers. What is interesting that initially they have a program counter as a part of the register file, which allows relatively interesting tricks, but at the moment of execution out of order and so on, it started to be a big problem. So 32-bit ARM has this problem that it needs to decode if it is the instruction which has some manipulation with register 15, and for those we need to use all the tricks with branch predictors and so on, and it is complex. It has a link register where we store the return address and stack pointer, And they have added the option when you switch from the user mode, for example, to the system mode or to the interrupt, that some part of the registers is switched, that you see some shadow version of those registers. It has big advantage, for example, if you switch from the standard mode to the fast interrupt, that basically if you can strive with this subset of the registers, then you can execute a fast interrupt routine without any storing the previous state, and because the return address is stored in the link register, then you branch to the link register and return back to the user mode. So it is very cheap to switch to those modes. But in the case when you switch to some more complex mode, then this switching of the registers makes things in the fact more complex than useful. There is, in this case, we have current processor status registers and safe processor status registers and so on. What is interesting on the ARM is that they added a barrel shifter on one input of arithmetic logic unit. So you can use another register or immediate value to shift data left or right or rotate data on one of the input of the arithmetic logic unit. So such combination, if you need to compute some address, which is some base plus some index, and that index is multiplied by the size of the element in the array, then it works quite well. And you have only 8-bit immediate values, possibility to encode into the instruction, but you can shift it to the left and so on. So again, you can build a quite interesting set of the constant, and it is relatively optimal. And you have the more addressing modes. We look at this later. Again, it has a status register which keeps the flags in this part, which are accessible even to the user. So you know what was the result of previous arithmetic logic operation. And then there is another part which is accessible only in the system mode, which allows to disable interrupts, fast interrupts, allows processor to switch to TUP mode and so on. And it has this set of different modes with that relatively complex switching of the registers, which I think is not the best option. That simple option that you have the exception PC and store the value there is, which is used on the MIPS and RISC-V is simple. So we are almost at the end. Those are the different processors which can be used for different application and so on. And it seems for a long time that there will be no other significant player, but then there came a different processor. Anyway, you see that Intel is good for mobile chips, and ARM is good for the mobile chips, excuse me, and Intel cannot sell the too complex processor in the mobile segment. On the other hand, ARM has problem with the servers because it is tuned for the that small systems, and it has conditionalized instruction and so on. So it was not ideal for this. And IBM has good instruction set which can survive over 50 years in a binary compatible way. So you see that instruction set architecture matters, and that encoding of the instruction matters. And because this is where the programmer meets hardware and so on. So one of the newer processors is a 64-bit ARM system, and it uses a link register to store the return address and doesn't use a register banking for the switch to the exception. They have a simple exception link registers which holds the previous PC value, and it is up to the operating system to store this value somewhere into the memory. PC is separated from the register file, so it is not part of that register file like into the 32-bit ARM. It has 32 registers, or in the fact 31 64-bit registers which are general purpose, and then register 63, which is in the fact plays a role of those 0 register in the MIPS and another architectures. So again, 64-bit ARM is maybe more MIPS than the previous ARM. It has a limited addressing. It has only a 12-bit immediate value encoding, and it can be only optionally shift left by 12 bits, and no more. The rest has to be read from the memory. And interesting is that there are preserved a 32-bit operation which ignores the upper bits of the source registers and zero those bits of the destination. And ARM defines that if you want to lower a power consumption and the 32-bit computation is enough for you, then if you use a 32-bit instruction, that keeping of those bits at the 0 and not activated that part of the arithmetic logic unit which would be need for the full 64-bit instruction, then it helps to preserve the power and lower the power consumption. For sure, you have even 64-bit instruction, but they can be a little more expensive in the power consumption consideration. They have omitted that encoding of the instructions which can be conditionalized, because for the 32-bit ARM, each instruction reserves 5 bits to conditionalize them. So short if then else segments can be encoded without the actual need of the branches. In the tomb mode, there is the IT if then else mechanism. They have retained some conditionalized operations, but very small amount of them. So basically you have, for example, this conditional move or conditional add operation and so on. They have 64-bit multiplication with 64-bit result, and another operation which can provide higher bits from the 64-bit multiplication. They have multiplication and add operation and so on. So it is the standard. The addressing use that 48 bits plus 1 for the addressing. So you have lower part for the user program, that upper part for the operating system. So it is the same as, for example, on 64-bit Intel. They can use that immediate offset can be multiplied by the access size. So this way, for the aligned variables, we can address a little more than that plus minus 4 kilobytes of the memory, because in this case, for that aligned values, we can access for the 64-bit variable the 8 bits, 8 times more. So we can access not plus minus 2 kilobytes, but plus minus 16 kilobytes of the memory. It has PC relative addressing. They do not use load multiple and store multiple registers, which was a relatively complex operation of the 32-bit ARM, which was too complex to implement in the superscalar way. So they allow only the pair of the registers access. They have some operations for the atomic access of the memory. And they lower number of the addressing modes. So they have only the base, then base register plus immediate operand, base register with some another register which is used as the index and can be shifted to the left by immediate operand. So this is for that accessing of the element of the arrays. It is possible to say that we want to keep the register only at the 32-bit width, that which is used as the index, and that it is extended. And then there is a pre-index, so and then post-index. Pre-index means that we use the base register, add some immediate value, 12-bit, access the memory location at that sum, and then move the register to that new location. So it allows to do the pre-indexing and to change the register. Other option is post-indexing, when we access a location pointed by the register, and then the value of the register is adjusted by the immediate value. And we can load PC relative values. So basically this allows to implement quite and encode quite interesting algorithms directly. And okay, it seems at the start that 64-bit ARM is not so interesting, but today you can see those ARMs from the Apple. And this Apple chip has been Apple A12 has been initially developed for the iPhone, but later it was extended even to the Apple M1, which is very interesting chip even on the desktop, because it can read up to 32 bytes and decode the 8 fixed encode instruction in the parallel. So in the single clock cycle, you can decode up to the 8 instructions, and it is not provided by the Apple, but according to the testing, it seems that part of the processor which is able to execute instruction out of order is able to hold up to 630 instructions, from which are up to 350 integer ones. It is able to run, it has in parallel ability to run I think 7 instruction on arithmetic logic unit. It has a special unit for the divide. For the multiplication, it is able to finish 2 instructions in the single clock cycle. And there is ability to run up to 3 load operation or 2 store operation in those combination in a parallel to access a cache. There are depth of the load queues and store queues and so on. So it seems that it is really powerful chip, and you can see that thanks to the RISC implementation and clean implementation and easy decoding of the instruction, they have increased the throughput something like 3 times in last 5 years, and Intel on the single core is able to increase the throughput by 28% only. So it is relatively interesting comparison. And today, not only the Apple can do interesting chips on the ARM, but Fujitsu, which used a Spark cores to build supercomputers, has used ARM 64-bit chip and implementation, and their designers was able to build a 48 cores processor with 4 assistant cores on the single chip, which has scalable vector extension and single instruction multiple data extensions, and has high bandwidth memories and so on. And this chip is a chip which allow them to achieve the rank 1 in top 500 in the 2020. So this is the chip based on the ARM which is most powerful K computer of the year 2020. Okay, if you look there for the lesson learned again, it seems that the too complex processors has then problem to extend and increase the throughput when we want to process instructions faster. So it was a problem, and IBM has picked those complex instructions for the PC. Today we use SRAM for instruction cache. If we simplify the instruction set architecture, then according to the original computation in 80s of the team of Professor Peterson and Hennessy, it was the competing teams, they did decide that it would be necessary to have a little more instructions, that basically you need to use for RISC instruction where a complex instruction processor can use only the 3. But because you can execute the instruction about 6 times faster when they are simpler, then they decide that it worth to build the RISC processor which will be 4 times faster than the contemporary CISCs. So it is for the 80s. And they have been right, and today all internal architectures, even including MIPS, including Intel, is based on this. On the other hand, today, this is this era of CISC, then the RISC has led and allowed to increase the throughput on single core. Then it seems that throughput increase on the single core is problematic, and today the increase of the throughput on single core is really big problem. So we need to go to the parallelism, and this means that you need to learn how to use efficiently memory, how to synchronize the stuff, to not overload the throughput of the buses and so on. Anyway, Professor Peterson still teach the computer architectures, and in 2010 they work on some experimental design and want to extend the processor core and test some options, and they found that they cannot use the MIPS for the latency problems, Intel licensing and complexity and so on. So they decide that they try to implement a new architecture. And one of these students, Kersten Arsanovic, has started to design a RISC-V, because Peterson designed a RISC-1 in 80s. So this is RISC-V, the 5th generation of the RISC. And interesting is that, okay, their plan was that it would take something like 3 months, and then they can start to do the research. In the fact, the architecture development took 3 years or more, but today it is BSD licenses, so you can reuse it freely. It is already supported by mainline C compilers, GCC, LLVM, binutils, Linux kernel, emulators. It is simpler than Spark, so even that it is Professor Peterson's work, he decided to look more for his competitor, Hennessy MIPS, than for his initial Spark, because it was too complex, so they use more MIPS-like encoding of the instructions, and they do not use registers windows and so on. And today there are many implementations, and already 20 or 30 implementation on the silicon. And what is nice, that full documentation is freely available, so you can look at the RISC-V Foundation repository and site. There is a list of the authors, and this design is very well described and very well thought through. So basically, if you read the specification, then in each other processor, we are perfect, we have done maximum, and this is perfect for this program and so on. In this case, they provide the analysis. ARM does it this way, Intel does it this way, we can do it this way and this way. And we choose usually the simplest solution which is possible, because it would not block increase of the throughput in the future. So it is relatively very simple processor which allows implementation which can be small or complex but fast. And it is classic design, so 32-bit register 1 is directly tied to 0. It has source register 1, source register 2, and destination register operands. And what is important, that those encoding is at fixed position. So it is what you have seen in the previous lectures, because this year we have switched to RISC-V already. So it is even the repeating for the exam now. And so they are kept at the same location, and at the end we use those parts of the instruction encoding, those bits which are not used for the source or destination register for the immediate operand encoding. So it has non-regular encoding of the immediate operands, but it is not so big problem. Program counter is not part of the register file, so it is separate. It has a PC relative addressing, and when they define the architecture, it is defined that it has ability to use the same encoding of the instruction for 32-bit, 64-bit, and 128-bit processor with the general purpose registers of this size. It has that reserve space, and now even a defined 16-bit encoding of those most used instruction. It can be extended by the floating point unit with single, double, and even quad encoding. So you can have even 128-bit floating point numbers. For some scientific application, it can be important. And they use, instead of single instruction multiple data, they provide another way how to have a scalable vector size. And in the fact, today ARM is taking the solution which was provided by RISC-V. And even Intel today has licensed cores from the Arsanovich and so on. So the architecture is simple. We have that 32 integer registers. Register 0 is fixed on 0. The size of the registers is given by the xlen parameter. So you can have a program which can run in 32-bit or 64-bit mode and so on. Program counter. For the floating point, we can have those 32-bit, 64-bit, on 128-bit, so it has flen. We have no status register for the user mode and for the integer operation. So in this case, we need to use a compare directly in the instruction, in the branch instruction. But for the floating point, we have there the special control and status register, because for the floating point we want to keep some exceptions and information about the overflow in the operation, underflow, and so on. So in this case, the separate status register has advantage. You have already seen that 16-bit encoding can have all the combinations on the lowest 2-bit except the 1 and 1. So basically, the least significant bit defines the encoding length. And there is defined the scheme that if the last two least significant bits are 1, 1, then the encoding is not 16-bit. In the fact, it is usually 32-bit. But again, there is reserved some combination, all the ones in those additional bits, which allows to encode the part of the code space to 48-bit or 64-bit and so on. So they are prepared, even that it is RISC architecture, they are prepared even for the longer instruction if it is really necessary. And there is interesting that source operand, source register, is for each instruction in the same location. Same for the second source operand and destination operand. And you see that if the second source operand is not used or it is immediate, it is encoded here. But at the moment when we have a store word instruction, then we need two source registers. So this part which would overlap with the second source register of the immediate operand is moved here. So the decoding of the immediate operand is more complex, but there is quite a lot of time in the pipeline to decode the immediate operand, because you have main problem to find the interdependencies based on the registers used as a destination and source operand between two instructions. And this one can be decoded very easily without the multiplexers and so on. So it has a relatively nice features. And for example, for the branches, there is a little another mismatch between the encoding, because we know that we do not need a bit 0, so because we can branch only to the even addresses, so that bit is used as a bit 11 to put here, so it extends the branch range than if it is fixed to 0, and so on. So immediate encoding is a little problematic. There are more different implementation. The architecture is fully free for academic and commercial use and so on. And there are even open source implementation. There is a boom implementation, which is superscalar, can have some issue window, reorder buffer, and then multiple computational units, and reorder file for the registers. It is written in the Chisel language, and it is interesting that it allows to build different processor from the same source basis with different computational power and so on. This is one of the first RISC-V chips, Hi-5, of the first which is able to execute even and run operating system like Linux and so on. So it has 4 cores plus 1 for the management, 1.5 gigahertz. It is 64-bit processor with integer, floating point, atomic, and so on, and compressed instruction set. It has a 39-bit virtual addressing, and then there is one support chip, and this board is with some memory and so on. So it is okay. It is not so powerful like PC, but it is more powerful than some Raspberry Pis and so on. There is the internal architecture. We have there already integrated a different peripheral, SD card, and so on. And then there is another chip. It is from the microchip, Polar file, and it is equivalent to the Zinc chip which you use here in our course. But in this case, it's 4-core RISC-V, and again, 1 support core RISC-V for the system management. And in this case, we have there again a relatively large area for open peripherals implemented in the FPGA. And for example, we can have this Starlight processor. It is again RISC-V, which is small processor, but it runs quite well, so you can look at some information. There are more projects. We are in contact with the companies in the Brno town in Czech Republic who develop RISC-V processors, and we have a request to provide them contact to the students who want to develop a processor who has interest in this area. So I have more requests and people interested in in cooperation with university, who really do the actual development. In the fact, in our country is the Kodasip company, which was one of the founding member of RISC-V Foundation. There is an expressive, very cheap chips development team, which builds RISC-V systems. We have supported some Nutix drivers for them, for Nutix operating system, and so on. You can find a lot more in those different channels and so on. So, it is for today. Thanks for your attention.